All right, guys. Here's the warm up for today, and you're gonna watch it. You're gonna fill it in like normal. So, go ahead and find your bell ringer. It says watch the following video on the Big Bang, and you only have to write in the question 3 things about cosmic background radiation, because we're gonna watch it real quick, and then you're gonna fill it out. Okay, so let me present and then we'll watch this. And let me make sure my sound is all the way up.
If you look up at the night sky in any direction, it's all the stars and more stars.
How loud is this? All right.
13.7 billion years to reach Earth. It's the oldest and most primeval light in the universe, a picture of our cosmos in its hot younger years, and it's called the cosmic background radiation. Of course, you can't really see this light with your naked eyes because it's in the microwave band of the electromagnetic spectrum, but it is visible to radios and radio telescopes, and even makes up a small portion of the salt and pepper on an analog TV. Where does this luminescent background come from? Well, just after the Big Bang, the entire universe was still so small it would have been very dense, scorchingly hot, and because it hadn't yet had time to get rough and uneven, it would also have been scrumptiously smooth. For a while, things would have been so sweltering that electrons didn't settle down as parts of atoms or molecules, but instead roamed freely in a kind of red-hot cosmic soup. That soup would have had lots of light bouncing around it too, scattering off of electrons and protons like a hall of mirrors. However, as the universe expanded, there was less and less energy to be had in any one place. And when things had cooled to just below the temperature of the sun, pairs of electrons and protons no longer had the energy to resist each other, and they fell into the electromagnetic embrace we call the hydrogen atom. These electrons were so enamored by their new proton love interests that they effectively began to ignore all the light bouncing around them. So with fewer free electrons for light to interact with, the universe suddenly became transparent, and all the pent-up light was sent forth in whatever direction it had been headed after its last scattering, doomed to travel alone and unnoticed through the cosmos. That is, until it bumps into something solid. When we finally see it here on Earth, this light has been stretched so much by the 13 billion year expansion of space that, like a record slowing down, its frequency and color have shifted from the original sunlight white all the way to cool microwaves. Thus, it's often called the cosmic microwave background radiation, or CMB. And just as we can tell the temperature of a red or white-hot iron from its glow, this light tells us the temperature of empty space, currently around 2.725 Kelvin, or minus 270 degrees Celsius. However, the universe isn't exactly 2.725 Kelvin in every direction. If we look closely, there are small and seemingly random but noticeable bumps all over the place, kind of like milk that's starting to curdle. Our best understanding is that these cosmic curds formed as quantum fluctuations in the otherwise creamy infant universe, and then began to coagulate as the universe cooled and expanded. It's hard to overstate just how small or unbumpy these fluctuations of temperature and density were to begin with. The hot or cold spots were only hotter or colder than their surroundings by a factor of about 1 in 100,000. That's like noticing that a bacteria makes a beach ball bigger. But while this clumping of the universe initially resulted in small variations like the ones we see in the CMB, later on the chunky curds of primordial soup attracted each other gravitationally, and they ultimately coagulated and coalesced to form all of the massive structures in the universe that we see today, like planets, stars, galaxies, and superclusters of galaxies. So when we look up at the night sky past those galaxies and see the ancient light of the cosmic microwave background radiation, we're literally seeing the starting point, the proverbial cream, if you will, from which the starry curds of the universe congealed. Or quite simply, proof that the moon really is made of cheese.
Okay, so let's get out of this. Excuse me, escape. All right, so 3 things about cosmic background radiation. One thing you can write down is that it is the energy left over from the Big Bang. Okay. Another thing is that it is energy. So it used to be really, really hot when it started, but now it has stretched out and cooled down. And a third thing is that you can write down is that as it cooled down, it became matter, and that matter clumped together, and that's what gives us first of all, hydrogen. That was the first element to form, but from that hydrogen, elements or other elements and galaxies and things like that. So I will write that down. Where will I write that down? On a doc so that you can write it also. Where's my new button? There it is. New. All right, so one thing was formed at the birth of the universe. 2, it used to be very hot and a different wavelength as it moved or as it cooled, as the universe expanded, it cooled and stretched the energy to microwaves. And then 3, as that energy cooled, protons and electrons could combine to form hydrogen and eventually everything else. Okay, that's your answer. You can pause me, you can copy that down, and then you need to move on to the next video. All right, have a good day.